This is the introduction to exercise 3.5 on inverse functions. Again, the idea of inverse functions is looking at if we reflect our function across the y equals the x line. So I'm just going to read through this component and then we'll go from there. An inverse function inverts the value of x and y. Later on, I'm going to show you what the appropriate notation for this is. Okay, a lot of students end up writing the wrong notation because it can get confusing. I'll show you the appropriate notation you can follow through with. This can only happen if there is only one value of y for each value of x and vice versa. In short, a function must be one-to-one. I'm going to give you a very basic example that we're all pretty familiar with. If I said, my function looks like this. For every y value, is there only one x value that can reach that y value? Yes. So there is an inverse function. And if I was to draw a dotted line across like that, my inverse function would look like this. Probably not as ugly, but it would look like that. It exists. If I have something that looks like this, that is not a function. Right? In fact, it's called a relation. Right? Basically, the idea is that for the same y value, there are multiple x that could get there. And for the same x value, there are also multiple y's that could get there. But basically, there is no inverse function for this. The idea we're focusing on with this point, where there is only one value of y for each value of x, is if I have a function that looks like this. If I was to then do the same reflection, Abigail, if I was to do the same reflection and do the dotted line here, and try my best to reflect it across, it's going to look something like this. In this case, that's not a function. If you were to try and calculate that, you'd end up with having to have two separate functions. But in general, the idea we're focusing on is, I'm going to erase this so we can see, only if there is one value of y for each value of x, and vice versa. In short, it must be a one-to-one function. For every x value, there must be one y value. Inverse function, f inverse, is defined by f inverse of x equals to y if f of y equals to x, and we've flipped it over. I'll show you the notation to do that. There is also a special relationship between the domain and range. You probably already know this by now. The domain of our original function is going to be the range of an inverse function, and the range of our original function is going to be the domain of our inverse function. It just switches, because we're switching the x and y values. Additionally, f of the f inverse is just x, and of course the inverse of just the original function, again, apologies, is just x as well. Great. Let's put that into practice. So very briefly, we're just going to look at this function here, which says sketch the inverse function on y equals x, 2x minus 1. We take this both ways. It's a very basic function. This is more just as a quick example. But we can try and find the equation of the inverse, or we can just sketch the original and then flip it across the, flip's probably not the right word, reflect it across the y equals to x line. Let's take that second approach, and we'll do the algebraic approach in the second example underneath. If I sketch my y equals to 2x, I'm going to try my best to make it look accurate without putting too much effort in. I know that it's -1, so my y-axis intercept is going to be there, and it's going to look something like that. Of course, that point is going to be 0, -1. This point here, I'm assuming we're okay with just writing a half, 0. We already know that. If I then try to find the inverse by, let me try that again, see if I can draw that a bit straighter. There we go. If I then try to find my inverse by reflecting against the line of y equals to x, my new equation should look something like this. Hopefully, a bit better than my drawing. Then, all I need to do is find these values here, right? Because it's inverse, what is this one going to be? It's going to be 0, a half, and this one, what's that one going to be? -1, 0. Easy. Pretty straightforward. Great. Let's move on to the slightly more difficult one. Let's look at what a question regarding inverse functions would look like. Find the inverse of each of the following functions, and there's multiple examples, but we're just going to go through maybe one or two. We'll go through two. Saying the domain and range of each. So, f of, I'm going from -2 to 1, approaches, going towards as a range of r, f of x equals to 2x plus 3. Something to note, right? I know it explicitly says that from -2 to 1. Now, this one right here is what we call a restricted domain. As an examiner or as an exam writer, I'm saying, Renee, you have to restrict the domain within these two. That is something I'm saying you have to do. It's not the maximal domain, because maximal domain is what it could be theoretically, but we're saying I'm restricting it here. This one here, that R is saying that the range could be all real values. It's not saying that the range for this function is all real values. Yeah, because after we restrict a domain, it's going to change our range. So what I'm going to do is I'm going to first write out the notation for what the process should be to get the inverse function. It's defined as f of x, so I have to use f. I'm going to write f inverse, and I'm going to do semicolon to show the examiner I'm writing the inverse. And then I can straight ahead replace x with y and the y with x.
Last year we were told that we had to write a little line that said inverse what? Do we have to do that?
It's a great question. I've never been told by an exam assessor, that you have to write that, but it'd be very beneficial in your case, absolutely. Rearrange. We get x minus 3 over 2 equals to y. I'm going to make my life easier. That's just going to be half of x minus 3 over 2. Now, of course, the original domain is -2 to 1. I'm going to write the original function using light blue. Now we know the domain is going to be where x is an element of -2 to 1. Now, would it be right for me to say the range is just going to be y as an element of all real values? No. If I look at this function at 2x plus 3, it's a straight line, it's a linear graph that goes upwards towards the right. If I substitute x equals -2, I'll get -1. So the range should be -1. If I was to substitute the other end of my domain, x equals 1, I would get 5. So the domain of my function, my original function should be from, the range, of my original function should be from -1 to 5. Please note that in this case, because it's a linear equation, I don't have to worry about whether there are turning points in the middle. If I give you a parabola and I restrict the domain, it's really important that you find where the turning point is, because that might be where your maximum or your minimum range is. But in this case, nice and easy, linear, let's move on. To find the inverse, we just switch it. So the domain would be x is an element of, and we go from -1 to 5, because I'm just copying the same one from above, but reflecting across. And the range, of course, is y is an element of -2 to 1. Any questions? Pretty familiar with this from last year? Okay. Let's move on. I'll leave that up on the screen for a bit. G of x is 1 over 5 minus x. I'm going to rearrange that. Equals to 1 over -x plus 5. Okay. What does that look like? Let's make our life even easier. Let's take out the negative, and we end up with -1 over x minus 5. Does that look a little bit more familiar? Okay. I know it's a rectangular hyperbola. I also know that it's got an asymptote at x equals to 5, because of course our denominator cannot equal to 0. So x equals to 5. And then because it's a negative, it's not going to be top right, bottom left, it's going to be the bottom right, top left. So it looks something like this. Okay. Now if I was to reflect it, and this is just to give myself a better idea. If I was to reflect it, so I'm going to go ahead and draw the y equals to x line. It's very faint. I'm going to zoom in. If I was to draw as soon as my, here we go. If I was to draw the y equals x line and I try to reflect it, it's going to end up looking like, actually, what's my asymptote going to change into? It's going to change into y plus 5, isn't it? Because we're switching x and y. So I'm going to end up drawing a line up here. And that's going to be y equals to 5. And we're reflecting. We're reflecting. Because I'm reflecting across, it's going to end up looking like, something like that, isn't it? Let's take an algebraic approach. Same thing, I'm going to write g inverse dot dot x equals to 1 over 5 minus y. Based on my understanding from literal equations from last year, I'm going to rearrange that. I can get 5 minus y times by x equals to 1 over, oh, that'd just be 1, sorry, because I'm timesing both sides of a 5 minus y. I'm going to divide by x, so 5 minus y equals to 1 over x, and then I'm going to end up with transposing. Y equals to 1 over x plus 5. I've skipped a step there, but I'm hoping you're okay with that. Great. Well, that lines up. 1 over x plus 5. Well, my graph has a positive translation in the y direction of y equals 5. That's my asymptote. What's the domain of my original function? What's the domain? What can't my x values be? Yeah.
All real values except x.
Perfect. All real values and using the backslash, x equals to positive 5. And the range would be all real values except what? Except 0. Thank you very much. And when we do the same thing for our inverse function, it's going to be the domain, as x is an element of all real values except 0. Oops. Except 0. And y, which is our range, should be all real values except 5. Probably notice a pattern by now, you just switch it. Any questions? Okay. In the next question, I'm going to quickly show you, I won't go through it, but in the next question you'll see h of x equals to x squared minus 2. Of course you're aware that's a parabola. If I was to just set it and say x squared minus 2, there is no singular inverse function that represents that. However, there is a specified domain. So have a think about, what does that change? What will that look like for the inverse function? Graphically, when I reflect across the y equals x line, what will that look like? Okay, any questions? All right.